All right, so looks like got a little late arriving crowd today. I'm sure more will join here in the next few minutes. Uh, so just kind of give you a look ahead before we get started today. Basically, we've got like two topics left. Um, what we're going to do today is start talking about stress due to combined loading. So we've looked at axial loads, we looked at bending. We're going to combine the axial and bending, and we'll do that today, tomorrow, and then the only other topic really that we'll have time to cover anyway is we're going to skip ahead to chapter 12 and talk about beam deflection. So that's basically what's left. We're returning to beams after our one-day discussion of pressure vessels. So today and tomorrow, combine loadings, and then next week, Monday, Tuesday, Wednesday, we'll do beam deflections. And then Thursday is our last day of class. We're not going over anything new on Thursday that would be on your last test. So that last day we'll just review anything that's going to be on your last test, which is the following Tuesday, August the 4th. And it is, I think it's at 8 o'clock that Tuesday morning. So that's what's coming up. Anybody got a question you want to bring up before we get started? All right, so in section 8.2 in your textbook is where you'll find what we're going to go over today. Now, we're not going to do everything that's in the textbook. You'll see an example in the textbook where you have not only combined axial loadings and bending, but also torsion and twisting. We are not going to include that. So we are, when I say combined loadings here, we're just going to cover combined axial and bending. All right, so if you happen to, like, you should be looking at the examples in the book. You know, if you see one that also has torsion, don't panic and think, well, he didn't do one like that in class. That's because we're not we're not doing that. I don't hold you responsible for that. So no twisting. So no torsional loadings combined. We're just going to do axial and bending, and it's going to be really, really straightforward. Basically, we're just going to use superposition and just add the two things that we've already discussed. You know, we already covered this, right, for an axial load. And if I've got a member and we'll assume tension here, but again, it doesn't matter. It's either going to be tension or compression, one, right? And if you cut this member, let's see. Anyway, look at the left side. We saw that we have again, this is assuming that we get far enough away from the end where we don't have any stress concentrations. We're going to a nice uniform stress distribution. It's supposed to be sigma. It's just P over A. So it's just whatever that normal axial force is divided by the cross-sectional area. That's the normal stress acting on that cross-sectional surface area. Right? So we did that back early this semester. One of the first things we did. More recently, we talked about bending. So in this case, we have this member. And we applied this bending moment. Well, that caused a normal stress on the cross-sectional surface area as well. Right, so again, if we come in here somewhere and cut this and look at that cross-section, right? We said there was this surface where the stress was zero, what we call the neutral surface, if you're looking longitudinally down the beam. And if we have a moment in this direction, it's going to cause compression up here on, in this case, the top. This would be a compressive normal stress. And if the moment is acting in this direction, it's pulling or stretching the bottom, and so we're going to get a tensile normal stress anywhere below that neutral surface. And so our stress distribution looks something like that. And if you looked at the actual cross section, I'm just again assuming it's rectangular because it makes it easy to draw. We said that neutral surface is going to coincide with where the centroid on that cross section was. And this was our z-axis, which was also what we called our neutral axis, if you're looking at the cross section. And for this particular example, anywhere above that neutral axis is in compression, everywhere down below is tension. And that stress was given by this formula, minus my over I. Where y is the vertical distance away from the neutral axis, positive up. This I, that's the moment of inertia about that neutral axis, or the z-axis. In the direction I've got shown here is what we've defined to be a positive moment. And so this was the formula we used to get the normal stress due to bending. Well, we're just going to use superposition here. We're just going to add these together. Right, so maybe I'll draw, let's say let's look at a 3D picture. And again, just assuming a rectangular cross section for simplicity and ease of drawing. All right, my coordinate system oriented like so. Again, x is the longitudinal direction. The origin of my coordinate system is at the centroid of that cross-sectional area. This is the z-axis, or the neutral axis. And, well, scratch that for now. You're going to see that's going to change in a second. So let's assume we apply an axial force. I'm going to get different colors. So let's go blue here. Got an axial force P, and we're also going to apply a moment. So we're going to do both. Or again, if you look at it, 2D picture might be clearer, I don't know. So what we got is this axial force P as well as a bending moment. Right, so we're applying both. Right, but all we're going to do is just add these together. So what we're going to get is just the sum of these two. Right? We're going to get this normal stress due to the axial force, and we're going to get this normal stress due to the bending. Right here, sigma is minus my over I. We just add those together. And what we'll get is a stress distribution. And I'll emphasize, it may look like this, it may not. It actually will depend on the magnitudes of these two things when you add them together. But this would just be, for example, all right, so our coordinate system, it doesn't move. It stays where the origin's at the centroid. But you're going to find the neutral axis is not going to be at the centroid anymore. Right? If you add these two together, right, by definition, the neutral axis and the neutral surface is where the stress is zero. And that's not going to be at the centroid anymore. When you add these two together, just look at the top surface. If this is indeed in tension and this in compression, when you combine those, you're going to get something smaller. And you're going to hit zero somewhere other than the centroid. So it might look something like this. So here's where our neutral axis and neutral surface would be. That's where the stress is zero. That's not going to be at the centroid anymore. But this normal stress we get is just the sum of these two, P over A minus my over I. We're literally just adding the two things together. Simple as that. So if we've done the axial stress, we've done the bending stress. If you can do those two, this should be easy. Because all we're doing is just combining and adding them together. Now, I mentioned the neutral axis is not at the centroid anymore, but just to make clear, you understand, keep your coordinate system at the centroid. We're not moving our coordinate system. So our z-axis would be coming straight out of the paper through the centroid, same place it was up here. What moves is the neutral axis. Now, if you want to define where that neutral axis was, it's really easy. Just set stress equals zero and solve for y, and that would tell you where the neutral axis is located. I just mentioned that for information purposes. I'm almost 100% sure none of the problems that you're going to see in the book is going to ask you to do that and locate where that neutral axis is. Now, that might come into play later in some, depending upon your major and what structures courses you take. Might come up then, but not for this class. So for this class, you get the normal stress distribution just using this formula, keeping your coordinate system right where we've been placing it all along, and that is at the centroid. All right, now, as far as sign convention goes, again, it's the same as what we've been using, but just want to make sure everybody remembers this. It's basically based on right-hand rule as far as moments go. So again, if you're looking at the coordinate system, again, x the longitudinal, z is horizontal, and y is vertical. We define this to be a positive moment, right? A moment in that direction. And again, positive P, axial force. Again, positive for tension, negative for compression. And so if you use this sign convention, you plug in this formula, it will give you the correct stress and sign, either whether it's in tension or compression, depending upon where you're located on that cross section. using this sign convention and this formula. Now, I will point out that it's actually fairly common, and this is going to be strictly a personal preference, whether or not you want to think about it like this or not. Again, if you use this formula, right, then you got to use this sign convention. But it's fairly common for at least some engineers I've seen do this, is just base the signs based on tension or compression, right? So this would be an alternative to using the sign convention. Just base signs on whether it's in tension or compression. Again, obviously positive for tension, negative for compression. And so if you think about it like this, you might want to think about it as just say plus or minus P over A, plus or minus My over I. And then you're choosing those signs based on just looking at it. And if you can just look at it and tell it's in tension, you use a positive value. If you can look at it, you know it's in compression, you just put a negative sign there. And you're just working with the magnitudes for the moment and the magnitude for Y. You're not actually using the sign convention and putting in, a plus or minus for Y or a plus or minus for the moment. And again, it's strictly up to you. Some people see this real easily, and it maybe it makes sense to them, and it's quicker and easier. They don't have to worry about figuring out, is this a positive moment or a negative moment? Is Y positive or negative? They just look at it and tell, okay, I know it's tension. I know this is going to be positive. Or you can look at it and say, I know that moment's putting this point in compression. So you just put a minus sign there. Either way works. All right, so any questions before we work a problem?
So with what you just said, is it based off the top of the beam or bottom?
It depends on where you're getting the stress.
Okay.
If you're asked to find the stress at, say, this point, right? So looking at that point, I know a moment in this direction is going to cause compression, right? Anywhere above that. So this would be negative. If you're finding the stress at some point down here, that moment's causing tension at that point. I know this is going to be positive.
Okay.
Does that make sense?
Yeah, thank you.
Right. So it just depends on where you're calculating the stress. You should be able to look at the cross section in the direction of the moment and tell, is this going to be tension or compression? And that's what I'm talking about here. But again, if that doesn't make sense to you, use this sign convention and this formula. All right. Any other questions before we work an example? All right. Well, then let's try to do one. All right. So let me draw the picture first here. We've got a column, got a rectangular cross section. That's probably not real. Not too bad. All right, so let's see. This is 2 inches wide, and this is 6 inches. And we are going to apply axial force acting straight down. It's 10,000 pounds. Acting at this edge right in the center. So if this is 2 inches, this is 1 inch, this is 1 inch. right? So it's right on that outer, I can be looking at it this way, the right edge, right in the center. And we want to find the stress at a couple of points. Call this A, this B, and this corner we'll call it D. And what we want to do is find normal stress. We'll go with points A and B. We'll see, maybe after we do that, maybe we'll pick some other points and maybe, I don't know, we'll see. All right, so that's what our problem looks like. This column got a compressive force, axial load of 10,000 pounds pushing down on this thing. And we want to get the normal stress at these two locations, these two corners, the front left corner and the back left corner, if we consider this the front. But notice where that axial load is applied is not at the central one. Remember when we very first day we started talking about axial loads, one of our assumptions was that the axial load was applied along the centroidal axis, right? So way back early in the semester, we saw a problem like this, that 10,000 pounds would have been acting right here at the centroid. And I specifically mentioned that assumption was so that we did not have bending. It was just an axial load. Because what happens when you apply this 10,000 pounds, not through the centroid, you apply it over here at the edge, not only do you get the 10,000 pounds pushing down, right, this force out here, right, it's going to bend this thing. Right? It's going to create a moment in that direction. So you're going to get an axial load and you're going to get bending. In fact, let me draw a new picture, look at our cross section, and we need to put our coordinate system on here as well. Right, so if we cut it down here and we're actually looking at this cross section where A, B, and D are. I don't know, maybe we'll call this point back here. So my coordinate system, remember, it's going to be located at the centroid. And we'll take this to be Y, this to be Z, and my x-axis is the axial direction. So applying this 10,000 pounds out here at the edge is equivalent to applying that 10,000 pounds. And this is one of the reasons in statics, you talk about equivalent loading systems. Some of y'all, maybe it hasn't been that long when you took statics, and you might remember something about equivalent loading systems. Well, the two loading systems are equivalent if the forces add up to be the same and the moments add up to be the same. So you can take a given loading system and replace it with something that's equivalent as long as the force is the same and the moment's the same. So if we take that 10,000 pounds and move it to the centroid, as long as it stays 10,000 pounds, the forces are the same. But what's different now, if we put it here at the centroid, it's not causing a moment about the z-axis. Right here, when it's out here at the edge, it's causing a moment about this z-axis. And that moment, let's see, where I'll put it. Right, it's going to cause a moment in this direction. And the magnitude of this moment has got to be the same as the moment it caused when it was out there at the edge. Well, if this is 6 inches, this is 3 inches. So that moment is going to be 10,000 pounds times 3 inches. It's going to be 30,000 inch-pounds. Right? So I'll write this in. So it's 30,000 inch-pounds. So this force applied at the edge is equivalent to that force and moment applied like that. Any questions about that? Everybody understand where we got this moment, 30,000 inch-pounds? All right, well then, again, to get our normal stress, again, P over A minus my over I. So we know P, we know our moment. Again, Y is going to be the distance from our Z-axis, but we need to calculate what the cross-sectional area is and what the moment of inertia is, because this moment of inertia, this is the moment of inertia about the Z-axis. This is that moment is the moment about the Z-axis. All right, so we got our moment, we need area, and we need I. So the area, that's pretty easy to calculate. Again, this is 2 inches by 6 inches. So 2 times 6, 12 square inches. Well, we're getting to that. Nathaniel asked the question, why isn't P over A negative? Again, this is the formula. That's all I've done is written down the formula. When we go about putting signs in, we got 2 choices. Either we can use the sign convention, or we can just look at it and tell tension and compression. And we'll talk about both. But right now, I just wrote down the formula. We'll get to signs in a second. But we also need the moment of inertia about the Z-axis. That's the axis we're bending this thing about. And that would be 1/12. The base is 2, height is 6. So 1/12 base times height cubed. And I got 36. All right, so first way I wanted to approach this is let's use sign convention here. So if we're going to use our sign convention, P is negative, right? It's causing compression. It's in the negative x direction. Positive x, that way. It's in the negative direction. So we would have P would be a negative 10,000 pounds. Our moment, again, right-hand rule says this is a positive moment. Pick your right hand, positive thumb in a positive direction your fingers go. That would be a positive moment. This is in the opposite direction, so it would actually be a negative 30,000 inch-pounds. Now, if we're getting the stress at A, this would be YA would be that distance, which is 3 inches. It's in the positive Y direction, so this would be a positive 3 inches. And for B, this would be YB. Positive Y is that way. This is a negative 3 inches. All right, so if you're going to use the sign convention and plug in this formula, those would be the signs that we would use for P and M and Y, and when we plug in the formula. Any question about where those signs came from? All right, so we find the stress at A, again, it doesn't matter where you're at on the cross section. P is going to be 10,000. It doesn't matter which point where you're located. So it's going to be minus 10,000 over our area is 12 minus our moment is a negative 30,000. YA is a positive 3. It's a positive 3. And then I is 36. And you add those together. And so this first term, the stress is going to be negative due to the compressive force. And here at point A, you see I have a negative times a negative. It's going to give you a positive. That's saying that that moment's causing a tensile stress at A, which, again, you look at the direction of moment. Everywhere over here is going to be compression. Everywhere over there would be tension due to that moment. So the signs work out. And you add those up, and I got 1,666.666 PSI. And if it comes out positive, that means A is in tension. If this first term, the compressive stress due to our axial load was big enough, it could come out in compression. Now, to get the stress at B, the only thing that's going to change is Y. That's it. If you move to a different point on this cross section, the only thing that changes is Y. Moment doesn't change, I doesn't change, P doesn't change, A doesn't change. None of that changes. The only thing in this formula that's dependent on where you're located is Y. I see students do strange things, and I ask them to find the stress at a different point. They'll get a different moment. I have no idea why, but they do. They'll even calculate a different moment of inertia. I have no idea why. None of that changes. Okay, so I'll make sure that's clear. The only thing that changes is Y. So we still have minus 10,000 over 12 minus our negative moment. Only thing changes now at B, Y is negative 3. And we add those together, and obviously we're going to get a negative here because both of those come out negative. 3,333.333 whatever PSI. So point B down here is in compression. That's what the negative signs indicate. Again, the alternative, if you don't want to do the sign convention, right, you could just, by looking at this, right, I know P over A, it's a compressive force, right? So this first term is going to be negative, minus P over A. And for the my over I, I know that's negative because I know it's compression. Look at point A. If my moment's in this direction, everything above the z-axis is going to be in tension, right? If we bend it this way. So it's going to be plus here because it's in tension. And again, just put in the magnitudes, right? So forget about whether the moment's plus, minus, whether y is plus or negative, right? You just do minus whatever that force is over the area, plus the moment's 30,000. Y, the distance A is away is 3. And again, just doing magnitudes here. And then divide by I. And you get the same thing. It's just a different way to think about it, right? So what you're doing is determining those signs based on whether they're against compression or tension. And you're just putting in magnitude. If nothing else, it's a good way to kind of check yourself. Even if you are using the sign convention, you should be able to look at it and rationalize, hey, I got a negative times a negative. This is telling me that moment's causing tension at A. Look at the picture and see if that makes sense. if nothing else, use it for that to make sure you haven't made a mistake with any of your signs. All right, any question? So, well, let's do one more thing for we say, let's go, we'll call this point G. And let's say it's, I don't know, 1.5 inches below the z-axis. So if we wanted to calculate the stress at that point G, what's the only thing that's going to change? I'm asking in hope for a response if somebody wants to type in. What's going to be the only thing that's different or change if we get the stress at this point I call G?
Y.
And what would Y be equal to? Say we're using the sign convention.
Negative 1.5.
That's it. So it would be minus 10,000 over 12 minus a negative 30,000. This would be a negative 1.5. That's the only thing that's going to change. Right? That makes sense. So if you're asked to find stress at different points on the cross section, don't go doing a bunch of weird stuff. P, A, M, and I don't change. Right? And again, your choice whether you want to just look at it and say tension and compression, or whether or not you want to use sign convention. That's up to you. Just be careful with your signs either way. All right, any other question about this one? All right, well, let's do one more, and then it'll be a good place to stop. This next one I found in your textbook. Let's see if I can move my keyboard out of the way here. I don't know if I'm going to have to move. Well, I can get to it. All right. We're looking at this problem. It's one of the problems from the review problems. If you happen to have a textbook close by, it's on page 442. This picture of this gondola and the passengers. So maybe you see these a lot of times up in the mountains. Maybe it's taking somebody up the mountain, go skiing or something. I don't know, but it's again, it's problem 8R 8.8-4 on page 442. If you want to go back and look at it in more detail later. But I wanted you to see the picture because I'm just going to draw the free body diagram of this thing. I'm not going to try to redraw this picture. It wouldn't look pretty. But it says the gondola and the passengers have a weight of 1,500 pounds. Center of gravity here is at G, so it's in line with this vertical section AB. And it's got this sort of bent member, A, B, C, D, E. Says it has a square cross section. It's 1.5 by 1.5 inches. And it's pin connected at the ends. Determine the largest tensile stress developed in section AB. So between A and B, wants to know what's the largest tensile stress. And then up here at this section, between C and D, what's the largest tensile stress in that part of this member, bent member. All right, so everybody kind of got a good picture of what it looks like, and then I'm going to move the textbook, and I'm going to draw a free body diagram of this member ABCD. All right. So speak up if you don't want me to move the book. All right, let's try it. So this is again, this is R8-4, page 442. And as always, I'm sure my picture will not be to scale. All right, so this was A, B, C, D, and E. As I mentioned, the weight there was lined up with this member, so it's pulling straight down 1,500 pounds. And then we're going to have a support reaction up here. If that roller, rail, or whatever that thing was, guide that gondola was riding on, we're going to have a vertical support reaction there. We also got some dimensions here. So this horizontal bent portion sticks out 1.25 feet to the right there. This is lined up vertically. All right, so that's what the free body diagram looks like. And we were asked to find the largest tensile stress in sections A, B, and C, D. That's what we're told the cross section was square. It was 1.5 inches by 1.5 inches. Right, that's what the cross section all the way down this member, A, B, C, D, E, cross section square like that. All right, so that's our problem, our setup. We've got our free body diagram, and it's basically it's two problems. We're going to try to find what the maximum tensile stress is between A and B, and then we'll find what the maximum tensile stress is between C and D. Right, so what we're going to do is we're going to come over here and we'll do the easy one first. Well, they're both easy, the shortest one. Right? If we want to know what the largest tensile stress is between A and B, let's cut it between A and B. Draw a free body diagram. So we can look at everything above where we cut it, or we can look at everything below where we cut it. Well, here it's pretty obvious, hopefully it should be, that it's to our advantage and less work if we just look at everything below where we cut it. So we need to know what is this axial force, and I'll call it PAB, and what is the moment. I'll call it MAB. Because that's what we need, right? Remember, stress is P over A minus MY over I. Right? If we've got combined axial and bending, we have to combine and add those together. So we need to know what the axial force is, and we need to know what the bending moment is acting on that cross section. Well, I hope we can just, by observation, look at this. I know the forces got to add up to 0. Well, I only got 2, PAB and 1500, so PAB's got to be 1500. It's going the direction I assumed, right? It's in tension. Some of the moments got to be 0. What's MAB got to be? Again, I'm asking for a response here. What's MAB? 0. Good, Nathaniel, that's correct. 0. Again, if you saw the moments about this point, these two forces are collinear. The only thing that's causing moments MAB, and if they got to add it to 0, it's got to be 0. So between A and B, that's 0. So the maximum tensile stress between A and B is just, again, whatever PAB is divided by the cross-sectional area. So take 1500, it's square, 1.5 times 1.5. I calculated that somewhere. Where'd it go? 666.666 psi. And that's going to be everywhere on that cross section. That's where you're going to get that maximal tensile stress because it's only due to this part, moment 0. All right? Question about that? So same approach, except when we look between C and D, we'll find that the moment's not 0. All right? If we cut it somewhere between C and D, again, we look at everything below or everything above. Your choice. If you do everything above, you got to calculate what EY is. That's easy to find. Like you could get it just by looking at it. EY's got to be 1500. But it maybe if it wasn't so simple to get EY, you might want to stick with everything below that. Again, up to you. But let's. In here, at A, we got the 1500 pounds. B here, C. So here's where we cut it. So we want to know what's the axial force. I'll call it PCD. And what's the moment? Now keep in mind this distance is 1.25 feet. So just like we did up there, forces got to add up to 0. That force PCD is going to be 1500 pounds in tension again. The moment's not going to be 0 now. If we sum the moments, again, pick any point. Maybe if you pick this point O. Well, PCD goes through that point, but you got this moment, and then you got the moment caused by that 1500 pounds. It's causing a counterclockwise moment, so we need a clockwise moment, the same magnitude, so that they add up to 0. So it's going to be 1500 times 1.25, which is, I think I calculated that, 1,875 foot-pounds. Right, so maybe it might help look at this Z, Y, and X is axial direction. Now my picture's actually kind of skewed there because otherwise they were going to line up right behind each other. All right. So what we just found is we've got this force PCD, 1500 pounds, and we got this moment acting this direction is 1,875 foot-pounds. Those are the two loads acting on this cross section. So it wants the largest tensile stress. So looking at that cross section, at this cross section here, where on that square cross section is the maximum tensile stress going to occur? sooner you answer and we put the numbers in there, we can quit. Motivate you. Answer fast. Left side of the bar. Very good. Right? The axial force is causing the same tensile stress everywhere on the cross section. It doesn't matter. This goes back to what we talked about up here. But if this moment is acting in this direction, right, that moment is causing tension on this side and compression on this side. So that maximum tension is going to be anywhere along that left, or if you want to think of it as the left top, if you're, it's going to be on the outer edge, right? So that's where you're going to get your maximum tension. So let's put in the numbers. Now this was what, 1.5. So again, if this would be 0.75, 0.75. Again, this is our Z. This is our Y. This is where our maximum tension is occurring. So we're going to plug in Y as 0.75. So maximum tensile stress, CD, we get P over A again. 1,500 divided by 1.5 times 1.5, P over A. And again, I'm just going to do positive because I know that moment's causing tension over there. Right? So I'm not doing sign convention here. Moment is 1,875. Those are pounds feet. You need to multiply by 12, right, to get inch pound. And what, Y is 0.75. I was, oh, we didn't calculate I yet, did we? So I is 1/12 base times height cubed. And that, I think I computed that. Yeah, it's 0.422 inches to the 4. Oh, almost forgot about I. 0.422. Anyway, add those together, and that will give me the maximum tensile stress anywhere between C and D, and it's going to occur along that left side. And I got 40,654.8 psi. Significantly larger than what it was here. So, lesson to be learned from this particular example. Anytime, if you do this to a bar, you make this offset like this, you might want to think twice, and you better only do it if you really have to do it, because you can see, I mean, that's only like 1.25 feet. Look what it did to the stress. It went from 600 and something to 40,600 and something. Huge increase in stress, and then the reason is because of that bending moment that's created when you do that offset like that. All right? Any question about that example? All right, so we're going to continue this tomorrow, and what we'll look at tomorrow is what if we bend it about both axes? In other words, not just the moment about the z-axis, but what if we also have a moment about the y-axis? We bend it both directions. That's what you can look forward to tomorrow. But out of time today, and as always, I'm going to stop recording, but in just a minute, I'll be at a point where I can answer questions. If anybody sticks around, you're welcome to do so and ask questions.